December 19th, 1944. The Ardennes Forest, Belgium. Obersturmführer Karl Hoffmann pressed his face against the frosted vision port of his disabled Panther tank, watching through swirling snow as an American Sherman rolled past his position just 50 meters distant. The Sherman moved with a fluidity that seemed impossible given the terrain. Deep snow, frozen mud ruts, and scattered debris from 3 days of fierce combat should have reduced any tank to a crawling, lurching beast. Yet this particular Sherman glided across the battlefield like it was traversing a paved highway. Hoffmann had commanded Panthers for 3 years. He knew armor. He understood suspension systems, ground pressure, and the brutal mathematics of cross-country mobility. What he was witnessing violated everything German tank doctrine had taught him about winter operations. His own Panther sat immobilized, not from enemy fire, but because frozen mud had packed solid between its interleaved road wheels during the previous night's movement. The entire left side suspension was locked. It would take hours of work with blowtorches to free the wheels, assuming they could find fuel for the torches. The American tank disappeared into the tree line, its wide tracks leaving barely disturbed snow. Hoffmann would later write in his combat report that this Sherman, marked with a white star and the tactical number 3 to 7, represented something unprecedented in his experience. It wasn't the armor, which his 75mm gun could penetrate easily. It wasn't the gun, which was adequate but not fearsome. It was the way the tank moved, absorbing terrain that would cripple German vehicles, maintaining speed across ground that should have been impassable. What Hoffmann couldn't see from his frozen position was the suspension system that enabled this remarkable mobility. Beneath that Sherman's hull, a revolutionary suspension design had replaced the vertical volute springs that characterized earlier Shermans. The Horizontal Volute Spring Suspension, designated HVSS by American engineers, represented a fundamental reimagining of how tanks interacted with terrain. This system would force German engineers, already reeling from revelations about American automotive reliability, to confront another uncomfortable truth. Germany had built the most technically sophisticated tanks in the world, yet had never achieved the practical mobility American engineers had accomplished through methodical improvement of a fundamentally sound design. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Sherman with HVSS didn't emerge from revolutionary breakthrough or desperate innovation. It resulted from systematic problem-solving by American engineers who recognized limitations in their existing design and methodically addressed them. The original Sherman, entering production in early 1942, used a suspension system designated VVSS, Vertical Volute Spring Suspension. This system employed bogie units with paired road wheels mounted on vertical coil springs. The design was simple, reliable, and adequately supported the 30-ton M4 Sherman for which it was engineered. But as the war progressed, the Sherman grew heavier. Additional armor, larger ammunition loads, improved engines, and various modifications pushed combat weight toward 35 tons and beyond. The VVSS suspension, though reliable, began showing limitations. The ride quality deteriorated with increased weight. Track life decreased as narrow tracks concentrated ground pressure. Cross-country speed suffered as the suspension bottomed out more frequently on rough terrain. Most critically, the narrow 23-inch tracks provided inadequate flotation in soft ground, limiting mobility in mud, sand, or snow. American Ordnance Department engineers, along with designers, at Pressed Steel Car Company and other contractors, began development work on improved suspension systems in 1943. Their goal wasn't revolutionary redesign but systematic improvement. The resulting HVSS system retained proven elements from VVSS while addressing specific deficiencies through engineering refinement rather than radical innovation. The HVSS system replaced vertical coil springs with horizontal volute springs mounted parallel to the hull. Each bogie unit now carried 2 sets of dual road wheels, giving 6 bogie units and 24 road wheels total versus 12 wheels in VVSS. The springs themselves were larger and more sophisticated, providing greater travel and better damping characteristics. Most visibly, HVSS Shermans used new 23-inch wide tracks, later increased to 26 inches, nearly doubling the ground contact area compared to VVSS tracks. The engineering changes seemed incremental to casual observers. German intelligence analysts reviewing photographs of HVSS-equipped Shermans initially dismissed the modifications as minor improvements unlikely to significantly affect combat performance. They were catastrophically wrong. The cumulative effect of these changes transformed Sherman mobility in ways that would become painfully apparent to German forces during the final year of the war. The first HVSS-equipped Shermans reached the European theater of operations in August 1944. The M4 Shermans, quickly nicknamed Easy 8 by American crews, combined HVSS suspension with the excellent Ford GAA Vate engine and the improved 76mm high-velocity gun. Initial deployment was limited as production ramped up, and earlier VVSS models remained in widespread service. By December 1944, sufficient numbers had reached frontline units to make a tactical impact during the Battle of the Bulge. German forces first encountered HVSS Shermans during the opening phases of Operation Wacht am Rhein, the Ardennes offensive. The weather conditions, terrain, and tactical situation created perfect circumstances for revealing the new suspension's advantages. Heavy snow blanketed the Ardennes. Temperatures plunged below freezing. Secondary roads, forest trails, and open fields became quagmires of mud beneath the snow. These conditions severely hampered German armor. Panthers and Tigers, already suffering reliability problems, faced additional challenges from frozen interleaved road wheels and inadequate track width for winter conditions. Hauptmann Werner Schmidt commanded a company of Panther OSV-G tanks with the 2nd Panzer Division during the Ardennes assault. His after-action report, filed in January 1945, described multiple encounters with American tanks demonstrating unexpected mobility. Schmidt noted that certain American Shermans, distinguishable by their wider tracks and different hull appearance, consistently outmaneuvered his Panthers in close terrain, despite the Panthers' superior power-to-weight ratio and more powerful engine. On December 23, Schmidt's company attempted to exploit a breakthrough near Mannheim. 3 Panthers bogged down in a snow-covered field that appeared passable. Recovery attempts failed as additional vehicles became stuck, attempting to tow the disabled tanks. Meanwhile, American Shermans that Schmidt specifically noted had unusually wide tracks and modified suspension, traversed the same field without difficulty, firing on German positions from angles the Panthers couldn't reach due to mobility limitations. Schmidt's technical observations were remarkably detailed for a combat report. He noted the Sherman tracks were perhaps twice the width of our tracks, and that the suspension appeared to have greater travel, allowing the vehicle to maintain speed over terrain, requiring us to slow considerably. Most tellingly, Schmidt wrote that the Americans appear to have solved problems with winter mobility that continue to plague our vehicles. The 2nd SS Panzer Corps encountered similar situations throughout the Ardennes campaign. SS Obersturmführer Joseph Diefenthal commanded a platoon of Panthers in the 1st SS Panzer Division. In a letter intercepted by Allied censors, Diefenthal described his frustration at watching American tanks maneuver freely while his own vehicles struggled with terrain. The new American tanks with the wide tracks move through snow and mud that stops our Panthers, he wrote. Yesterday we lost 2 tanks not to enemy fire but to ground conditions. The Americans drove past our positions on ground we could not traverse. These field observations reached German intelligence services and technical branches by early January 1945. Senior engineers at Waffenamt, the Army Weapons Office, requested detailed examination of captured examples. The opportunity came sooner than expected. On January 4, 1945, elements of the 6th Panzer Army captured 3 HVSS-equipped Shermans near St. Vith. 2 were damaged beyond mobility, but one M4 Shermans was taken intact when its crew abandoned the vehicle after throwing a track while attempting to withdraw under German artillery fire. This particular Sherman, serial number USA 3084921, had belonged to Company B, 37th Tank Battalion, 4th Armored Division. The tank bore the nickname Thunderbolt, painted on its turret, and showed signs of hard combat service, with multiple patches welded over battle damage. German recovery crews, experienced in salvaging disabled vehicles, replaced the thrown track using the tank's own repair equipment and drove it 20 kilometers to a collection point at St. Vith. Oberst Heinrich Müller, assigned to the Waffenamt liaison team with 6th Panzer Army, personally inspected the captured Sherman on January 6th. Müller had engineering training and 3 years' experience evaluating captured Soviet equipment. His initial assessment, transmitted to Berlin the same day, noted several features of immediate tactical interest. The suspension system appeared fundamentally different from previous Sherman models, using horizontal springs and substantially wider tracks. The arrangement of road wheels, with 4 dual wheels per bogie unit versus the earlier Sherman's paired arrangement, provided greater ground contact. Most significantly, Müller observed that the suspension provides exceptional ground clearance and appears capable of substantial vertical travel. Müller recommended immediate transport to testing facilities in Germany for comprehensive evaluation. Authorization came within 48 hours, reflecting the importance German command placed on understanding American technical developments. The Sherman was loaded onto a heavy rail car at Bitburg on January 9th and began the journey to Kummersdorf, proving grounds south of Berlin, the same facility where other captured Shermans had undergone extensive testing in 1943 and 1944. The captured M4 A38 arrived at Kummersdorf on January 14, 1945, in remarkably good condition considering its combat service and capture circumstances. Test engineers immediately began systematic documentation. They photographed the vehicle from every angle, measured every component, and stenciled technical notations across the hull and suspension, just as they had with earlier Shermans. The designation Butapanzer 394 identified it as a captured vehicle 394 in the Kummersdorf testing inventory. Diplom-Ingenieur Franz Hauser led the technical evaluation team. Hauser had participated in testing of earlier Sherman variants and was intimately familiar with American tank design philosophy. He approached the HVSS-equipped Sherman with particular interest, recognizing immediately that this represented significant improvement rather than minor modification. His preliminary report, dated January 16th, noted that the suspension modifications appeared to address specific deficiencies identified in earlier testing of VVSS Shermans. The initial inspection focused on the suspension system itself. Engineers measured spring rates, suspension travel, shock absorber characteristics, and geometric relationships between suspension components. They disassembled one complete bogie unit to examine internal components and manufacturing techniques. They documented track design, paying particular attention to the wider track shoes and the end connector system that differed from earlier Sherman tracks. The horizontal volute springs immediately impressed German engineers. Each spring assembly consisted of a large coil spring mounted horizontally within a cylindrical housing. The spring compressed as the bogie arm pivoted, providing suspension action. German analysis calculated that each HVSS spring had approximately 50% greater energy absorption capacity than the vertical springs in VVSS systems. The springs also provided longer effective travel, allowing the suspension to absorb larger bumps and deeper depressions without bottoming out. The bogie arm geometry received particular attention. HVSS bogies used a different pivot arrangement than VVSS, providing improved kinematics that maintained more consistent track tension throughout the suspension travel range. German engineers recognized this as sophisticated design work, producing practical benefits. The arrangement minimized the tendency for tracks to come loose during severe suspension movement, a problem that occasionally affected earlier Shermans and frequently plagued German designs. Track analysis revealed engineering choices that reflected American manufacturing philosophy and tactical priorities. The 23-inch wide track, standard on early HVSS Shermans, provided nearly double the ground contact area of 16-inch VVSS tracks. Later production, German engineers learned from intelligence reports, used 26-inch tracks providing even greater flotation. The tracks themselves used different construction than earlier models, with extended end connectors and reinforced guide horns that reduced track throwing incidents. German test engineers calculated ground pressure for the HVSS Sherman at approximately 10 pounds per square inch with 23-inch tracks, dropping to 9 pounds per square inch with 26-inch tracks. By comparison, the Panther AUSF-G generated approximately 12 to 13 pounds per square inch despite its wider tracks due to its heavier 45-ton combat weight. The Sherman, at 35 tons with HVSS, achieved better flotation than Germany's most advanced medium tank. The practical implications were obvious to anyone familiar with cross-country mobility. Lower ground pressure meant better performance in soft ground conditions, including mud, sand, snow, and soft soil. The Sherman could traverse terrain that would bog down German vehicles. It could maintain higher speeds across rough ground because the tracks didn't sink as deeply. It could operate in conditions that would immobilize Panthers and Tigers entirely. Initial automotive trials began on January 18th. Test drivers, experienced with both German tanks and earlier Sherman models, took Thunderbolt through basic mobility exercises on Kummersdorf's testing courses. The difference between HVSS and VVSS suspension became immediately apparent even on relatively smooth terrain. The ride quality was dramatically better. The tank maintained speed over obstacles that would force earlier Shermans to slow considerably. The wider tracks provided noticeably better traction in turns and on slopes. Oberfeldwebel Kurt Richter, a test driver with 5 years' experience operating every German tank type, plus numerous captured vehicles, provided detailed observations. The improved suspension transforms this tank's cross-country performance, Richter reported. Earlier Shermans we tested had acceptable mobility but harsh ride quality over rough terrain. This new suspension absorbs bumps that would jar crew and equipment in both earlier Shermans and our own tanks. The driver can maintain higher speeds because the tank remains more stable. Richter particularly noted the suspension's performance characteristics during rapid maneuvering. When making sharp turns at speed, the suspension keeps all wheels in ground contact far better than our designs. The Panther tends to lift inside wheels during hard turns, reducing traction. This Sherman keeps its weight distributed across all road wheels throughout the turn, providing better control and reducing track-throwing risk. The test program expanded to include direct comparisons with German vehicles. Engineers brought a Panther OSF-G from the facility's inventory to run alongside the Sherman through identical test courses. The results provided stark visual evidence of performance differences that numerical analysis had predicted. On smooth roads, the Panther maintained a slight speed advantage due to its more powerful 700 horsepower Maybach engine versus the Sherman's 500 horsepower Ford unit. But on rough terrain simulating battlefield conditions, the Sherman consistently outperformed the Panther. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The obstacle course comparison proved particularly revealing. Kummersdorf's main obstacle course included ditches, vertical steps, log piles, craters, and steep slopes designed to test suspension travel, ground clearance, and overall mobility. Both tanks ran the course multiple times under observation by senior engineers, including Hauser, and several officers from the Inspector General of Panzer Troop Staff. The Sherman completed the course consistently faster than the Panther, typically by 10 to 15%. More significantly, the Sherman maintained higher average speed throughout because it could take obstacles at speed that forced the Panther to slow considerably. The HVSS suspension absorbed impacts that would damage the Panther's more rigid suspension or risk-throwing tracks. Test observers noted that the Sherman crew experienced far less violent motion, meaning they would suffer less fatigue during extended operations. The ditch crossing tests demonstrated capabilities that particularly impressed German observers. Engineers constructed ditches of varying widths to determine maximum crossing capacity. The Sherman, with its longer track contact length and better weight distribution through HVSS suspension, consistently crossed wider ditches than the Panther. The softer suspension allowed the tank to drape across obstacles, maintaining traction on both sides of gaps that would leave the Panther high-centered with tracks spinning uselessly. Vertical obstacle climbing revealed similar advantages. Both tanks could theoretically climb obstacles up to 24 inches high based on geometric clearances. In practice, the Sherman's superior suspension travel and track grip allowed it to climb these obstacles more reliably and at higher approach speeds. The Panther often required multiple attempts and careful positioning to surmount obstacles the Sherman cleared on first approach without hesitation. The snow and mud trials conducted in late January 1945 provided the most dramatic comparisons. Kummersdorf engineers constructed test sections replicating winter battlefield conditions. One section simulated deep snow over frozen ground. Another created mud conditions similar to spring thaw. A third combined snow, ice, and partially frozen mud to replicate the worst winter combat terrain. In deep snow conditions approximating what German forces encountered in the Palais Ardennes, the performance difference was shocking. The Sherman plowed through snow depths that completely immobilized the Panther. The wider HVSS tracks distributed weight sufficiently to prevent the Sherman from sinking into soft snow layers beneath the surface crust. The Panther's narrower tracks, despite being wider than earlier German designs, still concentrated too much ground pressure, causing the vehicle to sink until belly armor contacted snow and forward progress became impossible. Diplom-Ingenieur Hauser documented these trials with scientific precision. In snow depth of 45 centimeters over firm ground, the Sherman maintains forward progress at speeds up to 15 kilometers per hour. The Panther bogs completely at approximately 35 centimeters depth. In deeper snow reaching 60 centimeters, the Sherman continues moving, though slowly, while the Panther requires recovery. The American tank's ground pressure advantage translates directly into winter battlefield mobility our vehicles cannot match. The mud trials were equally devastating to German confidence. The test section consisted of wet clay soil churned to create conditions similar to spring Rasputitsa on the Eastern Front or autumn rains in Western Europe. Both tanks attempted to cross the section multiple times at various speeds and approach angles. The Sherman traversed successfully in every attempt, though with difficulty in the deepest mud. The Panther succeeded only twice in 10 attempts, both times requiring maximum engine power and careful momentum management. In 8 attempts, the Panther became stuck, requiring towing by recovery vehicles. The interleaved road wheel system that provided the Panther with excellent weight distribution and smooth ride on firm ground became a catastrophic liability in mud and snow conditions. Mud packed between the overlapping wheels, adding tremendous weight and creating resistance that overwhelmed the drivetrain. Frozen mud locked the suspension entirely, as Obersturmführer Hoffmann had experienced in the Ardennes. The test team documented this effect by deliberately driving the Panther through mud, allowing it to sit overnight in freezing temperatures, then attempting to move the vehicle the following morning. The results confirmed what field reports had described. After standing overnight in temperatures just below freezing, the Panther's interleaved wheels were completely locked by frozen mud. The engine could run, but attempting to engage the drivetrain resulted in immediate stalling as the frozen suspension resisted movement. Recovery required hours of work with blowtorches carefully heating each wheel station to melt the ice, a process consuming valuable fuel and maintenance time while leaving the tank completely defenseless. The Sherman, by contrast, showed no such vulnerability. Its simpler bogie arrangement with individually suspended dual wheel units prevented mud accumulation between wheels. Snow and mud might pack around suspension components, but critical spaces remained clear enough to allow movement. After identical overnight freezing, the Sherman started and moved immediately, requiring no special preparation or maintenance attention. Major Hans Becker, representing the Inspector General of Panzer Troops at the testing, filed a report that reflected growing alarm among senior German tank officers about comparative mobility. The American suspension system provides operational mobility under winter conditions that our designs cannot achieve. This is not a minor technical advantage but a fundamental operational capability gap. American armored forces can maneuver freely in conditions that completely immobilize our formations. The implications for combat operations are severe. Becker's report included specific tactical scenarios where HVSS mobility advantages would prove decisive. In fluid combat situations requiring rapid position changes, the Sherman could relocate while German tanks struggled with terrain. In pursuit operations after breakthrough, American armor could maintain pressure while German forces bogged down. In withdrawal operations, Shermans could escape across ground that would trap German vehicles, explaining the numerous intact captures throughout the Ardennes offensive. When American units fell back across terrain, their tanks could traverse, but pursuing German armor could not follow. The testing program expanded to examine other aspects of the HVSS system beyond pure mobility. Engineers evaluated maintenance requirements, finding that the horizontal spring arrangement actually simplified field repairs compared to vertical spring systems. A damaged HVSS bogie unit could be replaced by unbolting 4 mounting points and installing a new unit, taking approximately 2 hours with proper equipment. The Panther's torsion bar suspension required substantially more effort for similar repairs, often necessitating removal of multiple overlapping wheel sets and careful handling of highly stressed torsion bars. Track life analysis revealed another American advantage. German engineers calculated that HVSS tracks, operating at lower ground pressure and benefiting from improved suspension kinematics that maintained more consistent tension, would last approximately 6,000 to 8,000 kilometers before requiring replacement. Panther tracks typically needed replacement after 2,000 to 3,000 kilometers. The wider Sherman tracks also wore more evenly, allowing longer service before critical wear made replacement necessary. The spare track storage on HVSS Shermans demonstrated practical design thinking. The tank carried multiple spare track blocks mounted on the hull, easily accessible for field replacement. German tanks carried fewer spares in less accessible positions. Combined with longer track life, the American approach meant HVSS Shermans could operate for extended periods without supply chain support for track replacement, while German tanks required regular resupply of tracks even without combat damage. Oberleutnant Paul Fischer, a maintenance officer with extensive field experience, examined the HVSS system from a logistics perspective. His assessment highlighted advantages that extended beyond raw performance. The American suspension system requires minimal specialized knowledge for field maintenance. A crew with basic mechanical training can replace damaged components using common tools. Our torsion bar systems require specialized equipment and trained technicians for most repairs. In sustained combat, when specialized support becomes unavailable, this difference becomes critical. Fischer noted that captured HVSS Shermans, pressed into German service, could be maintained by ordinary mechanics without extensive training, while German tankers required weeks of instruction on Panther and Tiger maintenance procedures. The Americans design systems that ordinary soldiers can maintain. We design systems that require specialists. Their approach is operationally superior when specialist support breaks down under combat conditions. The captured Sherman underwent gunnery trials to evaluate the complete weapon system. While the main focus remained on mobility and suspension, German engineers maintained thoroughness by testing every aspect of the vehicle. The 76mm M1A1 gun mounted on this particular EZ-8 provided significantly better armor penetration than the earlier 75mm gun, though still inferior to German 88mm and 75mm high-velocity weapons. However, the gun's effectiveness was enhanced by the HVSS suspension's stability characteristics. The improved suspension reduced vehicle movement after firing, allowing faster follow-up shots. The better ride quality meant gun stabilization systems functioned more effectively over rough terrain. Test firers reported that accurate fire could be delivered at higher cross-country speeds than in German tanks, where harsh suspension motion disrupted aiming even when vehicles moved slowly. The gyro stabilizer system, which German engineers had examined in earlier Sherman testing, worked more effectively when paired with HVSS suspension. The single-axis stabilization in elevation allowed reasonably accurate fire while moving, a capability no German tank possessed. When combined with the smoother ride provided by HVSS, the stabilizer performed even better, permitting effective fire in situations where German tanks would need to halt completely. By early February 1945, Kummersdorf had accumulated comprehensive data on HVSS Sherman capabilities. The final technical report compiled over 200 pages and included dozens of photographs, detailed measurements, and comparative analysis. The conclusions were unambiguous and professionally stated, but represented damning assessment of German tank development priorities. The American HVSS suspension system represents a mature engineering solution to problems inherent in armored vehicle cross-country mobility, the report stated in its summary section. Through systematic improvement of proven designs rather than radical innovation, American engineers have achieved mobility characteristics superior to German vehicles across most terrain conditions. The system prioritizes practical operational effectiveness over theoretical performance maximums. The report detailed specific areas where HVSS provided decisive advantages. Ground pressure approximately 25% lower than comparable German tanks, providing better flotation in soft terrain. Suspension travel approximately 40% greater than Panther torsion bar system, allowing higher speeds over rough terrain. Simplified maintenance requires fewer specialized tools and less training. Resistance to mud and snow contamination that regularly immobilized German vehicles. Extended track life, reducing logistical burden. Improved crew comfort, reducing fatigue during long movements. The report acknowledged areas where German designs retained advantages. The Panthers' torsion bar suspension provided excellent ride quality on roads and firm terrain. The interleaved wheel arrangement distributed weight effectively when not compromised by mud or snow. German armor protection and gun power remained superior in direct combat. But the report concluded that mobility advantages provided by HVSS were strategically more significant than German advantages in direct combat capabilities. In modern mobile warfare, the ability to maneuver freely determines whether superior firepower and protection can be brought to bear effectively, the report argued. A tank that cannot reach the battlefield or arrives exhausted from struggling with terrain provides no combat value regardless of armor thickness or gun penetration. The American mobility advantage translates directly into operational effectiveness. Our vehicles cannot match under field conditions. The report made specific recommendations for German tank development, though everyone involved understood these came too late for implementation. Future German designs should prioritize mobility and reliability over maximum armor and gun power. Suspension systems should be tested extensively in mud and snow conditions before adoption. Ground pressure should be minimized through wider tracks and lighter weight. Maintenance requirements should assume limited specialist support and common tools. These recommendations essentially advocated abandoning the design philosophy that produced the Panther and Tiger in favor of the approach that created the Sherman. Several senior engineers appended personal comments to the report, expressing frustration that these lessons came so late. Diplom-Ingenieur Hauser wrote that the Americans appear to understand, through extensive commercial automotive experience, what German designers learned, only through painful wartime failures. Industrial maturity matters more than theoretical engineering knowledge. Their decades of civilian vehicle production taught practical lessons our tank designers never absorbed. Major Becker's addendum was more direct. We built tanks to win individual battles through superior firepower and protection. The Americans built tanks to win the war through superior mobility and operational sustainability. History will judge which approach was correct. Based on current battlefield situations, the judgment appears clear. The captured HVSS Sherman remained at Kummersdorf through February 1945, serving as a training aid and continuing to undergo specialized tests. As Soviet forces advanced toward Berlin, plans were made to evacuate the facility. Some equipment was shipped west to facilities in areas expected to come under American occupation. Other materials were destroyed to prevent capture. The fate of the captured EZ-8 is uncertain. It may have been pressed into improvised service during the defense of Berlin. It may have been captured by Soviet forces overrunning Kummersdorf. No definitive records survive. Other HVSS-equipped Shermans captured on western and eastern fronts saw varied fates. Several were integrated into German units, desperate for any operational armor, as German production collapsed in early 1945. The 10th SS Panzer Division operated at least 3 EZ-8s during fighting in Hungary in March 1945. These vehicles, originally from Soviet Lend-Lease shipments captured during German counterattacks, served in reconnaissance and exploitation roles where mobility mattered more than armor protection. German crews who operated captured HVSS Shermans universally praised their cross-country mobility. Unterscharführer Ernst Weber commanded a captured EZ-8 with the 10th SS Panzer Division during the final weeks of the war. In a post-war interview conducted by American intelligence officers, Weber described his experience. "I had trained on Panzer IVs, fought in Panthers, and briefly commanded a Tiger. The Sherman, with the new suspension and wide tracks, was the most mobile tank I ever operated. We could go places our German tanks couldn't reach. In the chaos of the final months, mobility meant survival. That Sherman kept us alive longer than any German tank could have." Weber's testimony aligned with reports from other German tankers who operated HVSS Shermans in the final desperate months. These weren't technical evaluations from engineers with measurement instruments and testing protocols. These were survival assessments from combat soldiers who understood that mobility determined whether they lived or died. When choosing between a Panther with superior armor and firepower, but questionable reliability and winter mobility, or a Sherman that would keep moving regardless of conditions, pragmatic soldiers increasingly chose the American tank. The operational implications extended far beyond individual vehicle performance. German armored doctrine relied on concentration of force, using superior tank quality to overcome numerical disadvantages. This approach assumed German tanks could maneuver to chosen engagement positions, concentrate for attacks, and withdraw when necessary. HVSS mobility advantages undermined these assumptions. American armored units could maneuver more freely, choosing engagement conditions favorable to their capabilities, while avoiding situations where German advantages in armor and firepower would prove decisive. The Battle of the Bulge provided clear examples of how HVSS mobility affected operational outcomes. German forces achieved tactical surprise and initial success, but couldn't exploit breakthroughs because winter conditions immobilized their armor. Panthers and Tigers that should have been spearheading drives to the Meuse River instead sat disabled by mechanical failures or bogged in snow and mud. Meanwhile, American armored units, including the 4th Armored Division, equipped with significant numbers of HVSS Shermans, conducted rapid movements that German commanders thought impossible in winter conditions. General George Patton's Third Army executed one of the war's most remarkable armored maneuvers, disengaging from offensive operations in the Saar, pivoting 90 degrees north, and advancing over 100 kilometers through winter storms to relieve Bastogne. This movement, completed in just 3 days under appalling weather conditions, would have been impossible without tanks capable of sustained high-speed movement across snow-covered roads and frozen fields. HVSS-equipped units led these movements, their superior winter mobility enabling maneuvers German doctrine considered impossible. German intelligence officers analyzing the Third Army's movements concluded that American armored mobility exceeded their previous estimates by substantial margins. Major Friedrich Wendt, assigned to Army Group B intelligence staff, wrote in a January 1945 assessment that American tank units demonstrate winter mobility approaching that of wheeled vehicles on roads, while maintaining cross-country capability far exceeding our tracked vehicles. We cannot match their operational tempo under current conditions. The Eastern Front provided additional evidence of HVSS superiority in extreme conditions. The Soviet Union received over 4,000 diesel-powered M4A2 Shermans through Lend-Lease, with later shipments including HVSS-equipped variants. Soviet tank officers, intimately familiar with winter warfare challenges and experienced with both Soviet and American equipment, quickly recognized HVSS advantages. The wider tracks and improved suspension provided better performance in deep snow and spring mud than even Soviet designs specifically engineered for Russian conditions. Soviet tank units often preferentially assigned HVSS Shermans to reconnaissance and exploitation roles where mobility mattered most. Guards tank armies advancing through Poland and into Germany in early 1945 employed HVSS Shermans as lead elements, relying on their mobility to maintain rapid advance rates. German units facing these Soviet thrusts captured several HVSS-equipped Shermans during brief counterattacks, providing additional examples for technical evaluation. Oberst Martin Dietz commanded a Kampfgruppe that captured 2 M4A2 HVSS Shermans from Soviet forces near Kustrin in February 1945. Dietz's unit immediately pressed both tanks into service, a decision reflecting desperate equipment shortages, but also recognition of the Sherman's capabilities. In his combat report, Dietz noted that the captured American tanks proved more reliable and mobile than our remaining Panthers. The wide tracks perform excellently in mud conditions currently prevailing. Crews adapt quickly to controls and express preference for operating these vehicles over German equipment. The preference German crews showed for captured HVSS Shermans represented the ultimate practical assessment. When given choice between German tanks with superior specifications and American tanks with superior operational characteristics, combat soldiers chose the Americans. Firepower and armor protection meant nothing if tanks couldn't reach battle or broke down after brief operation. Mobility and reliability determined whether armored units could execute their missions. HVSS Shermans provided both consistently. German tanks increasingly provided neither. The technical reports from Kummersdorf and field assessments from combat units reached the highest levels of German military leadership in early 1945. General Heinz Guderian, chief of the German General Staff, received briefings on American mobility advantages. His response reflected the hopelessness of Germany's situation. The Americans had systematically solved problems German industry couldn't address, even if given time and resources were no longer available. Developing comparable suspension systems would require complete redesign of German tanks and retooling of manufacturing facilities. Neither was possible with Soviet armies approaching Berlin and Western allies crossing the Rhine. Some engineers proposed emergency modifications to existing German tanks, attempting to incorporate HVSS principles. These proposals included wider tracks for Panthers, modified bogie arrangements, and improved suspension components. None progressed beyond preliminary design work. Germany's industrial capacity was collapsing under combined effects of strategic bombing, raw material shortages, transportation system destruction, and territorial losses. Factories that remained operational struggled to produce existing designs with degrading quality. Implementing new systems was impossible. The contrast between American and German industrial capabilities became starkest when examining suspension system production. American factories manufactured HVSS components by the tens of thousands, using mass production techniques refined over decades of civilian automotive manufacturing. The horizontal volute springs, bogie arms, road wheels, and tracks rolled off assembly lines in multiple factories with perfect interchangeability. Any HVSS component could replace any other identical component without fitting or adjustment. German suspension component production remained partially craft-based even in 1945. Torsion bars required precise heat treatment and careful fitting. Interleaved wheel assemblies needed individual adjustment. Components from different manufacturers showed variations that prevented true interchangeability. The production processes that created magnificent individual tanks couldn't scale to produce truly mass-produced vehicles with consistent quality. The HVSS system also demonstrated growth potential that German design lacked. The suspension could handle significantly heavier vehicles than the 35-ton EZ-8. Post-war development would see HVSS supporting Sherman variants exceeding 40 tons with additional armor and armament. The Israelis would use HVSS Shermans well into the 1970s, repeatedly upgrading guns and engines while the suspension continued performing reliably. German torsion bar systems, already stressed supporting 45-ton Panthers, had no capacity for growth without complete redesign. American engineers had designed margins into HVSS components, accepting modest weight and cost increases to provide capability for future improvements. German engineers, operating under severe resource constraints and pressure for maximum immediate performance, designed components to minimum specifications. The American approach enabled decades of service life and continuous improvement. The German approach produced vehicles that performed brilliantly when new, but had no development potential beyond initial specifications. The philosophical differences extended throughout both nations' approaches to armored warfare. American doctrine emphasized mobility and operational tempo, using speed and maneuver to offset firepower disadvantages. This doctrine required reliable, mobile tanks that could sustain rapid movements over extended periods. The Sherman, particularly in HVSS configuration, perfectly matched these requirements. German doctrine emphasized firepower and protection, seeking decisive engagement outcomes through technical superiority. This doctrine demanded powerful guns and heavy armor, leading to designs that sacrificed mobility and reliability. Both approaches had logic within their strategic contexts. Germany, fighting numerically superior enemies on multiple fronts with limited industrial capacity, needed individual vehicle superiority to achieve favorable loss ratios. The United States, possessing overwhelming industrial capacity and fighting coalition warfare with reliable logistics, could accept adequate individual vehicle performance if produced in crushing quantities. The problem for Germany was that American tanks proved adequate for mission requirements, while German tanks proved inadequate for sustained operations, regardless of impressive specifications. The HVSS Sherman represented the culmination of American systematic improvement philosophy. The basic Sherman design from 1942 was sound, but had limitations. American engineers identified specific weaknesses through combat experience and testing. then developed targeted solutions. The HVSS addressed mobility limitations without requiring complete vehicle redesign. The 76mm gun addressed firepower concerns using the existing turret and hull. The wet ammunition storage addressed fire vulnerability through simple modification. Each improvement built on a solid foundation, creating progressively better vehicles without disrupting production. German tank development followed a different pattern. Each new design attempted revolutionary improvement, creating completely new vehicles rather than improving existing ones. The Panther replaced the Panzer IV. The Tiger replaced heavy tank requirements. Each new design introduced new problems requiring solutions, creating cascading development challenges. The Panther's final drives failed, requiring redesign. The Tiger's interleaved wheels proved maintenance nightmares, yet the Panther adopted similar systems. Revolutionary approaches prevented the incremental reliability improvements that systematic development enabled. By March 1945, German tank forces had essentially ceased functioning as coherent formations. Fuel shortages immobilized vehicles regardless of mechanical condition. Spare parts became unobtainable as factories were bombed or overrun. Trained crews were killed faster than replacements could be trained. But mechanical unreliability and mobility limitations had been crippling German armor long before these final catastrophic failures. The Tigers and Panthers that looked so fearsome in propaganda photographs spent more time broken down than fighting. The Shermans that looked pedestrian in comparison kept fighting consistently. The final irony was that Germany possessed engineering knowledge to build reliable, mobile tanks. German engineers understood automotive principles as thoroughly as their American counterparts. The scientists and technicians at Kummersdorf, who tested HVSS Shermans, could have designed equivalent or superior systems given proper priorities and resources. But German military culture, industrial structure, and strategic situation prevented applying that knowledge effectively. Technical sophistication was mistaken for practical effectiveness. Impressive specifications were prioritized over operational sustainability. The result was magnificent failures rather than adequate successes. The HVSS Sherman wasn't the best tank of World War II by any single performance metric. Soviet 3485s had better armor and comparable mobility. German Panthers had superior guns and frontal protection. British Centurions entering service in 1945 had better overall balance of capabilities. But the HVSS Sherman was available in overwhelming numbers when needed, could be maintained by average mechanics with basic tools, performed reliably across all terrain and weather conditions, and kept fighting consistently from deployment through war's end. These practical virtues proved more valuable than theoretical excellence. German tankers who tested, fought against, and sometimes operated HVSS Shermans reached unanimous conclusions. The Americans had built a tank Germany couldn't match in mobility and operational effectiveness, not through revolutionary technology or secret innovations, but through systematic engineering improvement and industrial maturity. The wide tracks, horizontal springs, and refined suspension geometry represented straightforward solutions to well-understood problems. Germany had the knowledge to implement similar solutions, but lacked the industrial capacity, proper priorities, and time to do so effectively. The lessons from HVSS Sherman development influenced post-war tank design worldwide. The West German Leopard 1, entering service in the 1960s, emphasized mobility and reliability over maximum armor protection. The designers, many of whom had evaluated Shermans during the war, consciously applied lessons learned about operational effectiveness, mattering more than specification superiority. The resulting tank became one of the Cold War's most successful designs, serving with dozens of nations for decades. The story of German forces capturing and testing HVSS Shermans represents a final chapter in the larger narrative of American versus German armored warfare philosophy. It demonstrates how systematic improvement of fundamentally sound designs defeated revolutionary attempts to achieve superiority through technical complexity. It shows how industrial maturity and practical engineering trumped theoretical knowledge and scientific expertise. Most importantly, it proves that in sustained industrial warfare, the weapon that works consistently beats the weapon that works brilliantly, but rarely. The engineers at Kummersdorf, who measured, tested, and documented HVSS Sherman capabilities, produced some of the war's most honest technical assessments. Their reports acknowledged American achievements without excuses or propaganda. They recognized that Germany had lost not just the war, but the industrial and engineering competition that determined the war's outcome. The HVSS suspension was physical proof that American engineering had surpassed German capabilities in areas that mattered most for 20th century mechanized warfare. That truth, documented in classified reports circulated among German officers in the war's final months, confirmed what battlefield results had already demonstrated. Germany's technical sophistication couldn't overcome America's industrial maturity and systematic engineering excellence. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.